So hi everyone. I'll be talking about Tamagotchis and generators. Since I've already been introduced, I won't go through that spiel, but I'm a senior front-end engineer at ClassPass, and if you want to reach out to me on Twitter, my handle is girlcode. So how many of you had a Tamagotchi? Ooh, good portion of you. Awesome. Okay, so if you aren't familiar with them, Tamagotchis were popular digital pets in the 90s. They were handheld devices like this. And the game would start, an egg would hatch, and out would pop your Tamagotchi. And your job was to take care of it. So you needed to feed it, play with it, and clean up after it as it grew from a baby to an adult. And when it became an adult, you didn't know what type of Tamagotchi you were going to get, so that was like a really fun surprise. I had a Tamagotchi growing up, so I've nurtured some Tamagotchis to adulthood. Some didn't make it. That's okay. I really love this game, so I wanted to build a web version for myself. So my version, Tamagotchi, uses an SVG shell. It has controls for the user to interact with the Tamagotchi. And the game screen is built in Canvas. So if you've never played with Canvas, it's a ton of fun to play with. To draw on the canvas, we're going to query the DOM for the canvas element. And then we're going to ask for the context from the canvas element. So in this case, we want 2D. And then we're going to use context.drawImage. We're going to pass it an image and some other XY coordinates that I'm not going to get into right now. And it's going to draw the image to the screen. So you can see that my Tamagotchi has been drawn at the bottom. For all the animations in this game, sorry, I think the slides were a little out of order. For all the animations in this game, I used a sprite sheet. So at the bottom is the sprite sheet to bounce the Tamagotchi. So if I want the Tamagotchi to bounce up, and each sprite is 200 pixels, then I need to draw this at 0, and then 200, and then 400 pixels. And so that will bounce them up. And you'll also notice that I'm using context.clear before I'm drawing each frame, and that's to avoid this situation. So if you don't clear between frames, they just all draw like on top of each other. So we need to avoid that. Okay, so as that code was written, this is not going to work. It's going to draw really quickly, and it's going to draw so quickly and clear the frame so quickly that you only see the last frame drawn on the screen. So what I actually want is I want a delay in the animation. I'm looking for an old school, choppy, pixely animation like the original game. So to do this, I'm going to use set timeout to delay the animations. And so this works. So now you can see my Tamagotchi is bouncing up and down. I'm animating from frame 1 to 3, then back to 2 and 1 for a full bounce up and down. But I've now created an issue because my animations are now async. So how do I know when this animation stops and I can start another one? How do I avoid overwriting this animation with another one? How do I avoid a long delay between animations? So what I want is to resolve an animation and then handle another animation. And this sounds a lot like a promise. So promises represent eventual values. So I can run the animation code inside a promise, and when that resolves, I can kick off another animation. Since promises are thennables, that's when I can start kicking off that animation. And then I can run a chain of animations down. So for the first version of this game, I used promises. I created a general purpose animate function that takes in a draw function and the milliseconds for the delay. Animate always returns a new promise, and inside that promise, an inner function runs the draw function. So we delegate resolving the promise to the draw function. If draw resolves the promise and returns true, we're done. Otherwise, set timeout is called with the inner function, and another loop of this function occurs. Here, we use the animate function to create a bounce up animation. So we pass a function that draws the correct frame, clears the context, and increments the current frame. When the current frame is greater than the frame count, the promise resolves, and we return true. and this would stop the function from setting another loop in setTimeout. So now we can create a simple bounce function using our bounce up animation and our bounce down animation using the same animate function. And as you can see, the Tamagotchi bouncing up and down. All right, so with basic animations out of the way, let's move on to creating the main game loop. So when you're not interacting with the Tamagotchi, it does an idle animation like this. So it bounces up and down, moves to the left, moves to the right, bounces, so on and so forth. So to set up the loop, we're going to create a loop function. We're going to call the idle animation, and when that resolves, we call the loop function again. So it just keeps setting itself. Okay, so we got basic animations, we got the idle thing, like what else do we need? Oh, we need to resolve some issues. So we have some problems with how this has been done, and I discovered these as I was building this game. So, once upon a time, we used callbacks for async work on the front end, and this led to the dreaded triangle of doom, aka callback hell. And one of the things I noticed when building this game was that promises didn't really alleviate callback hell. You're still in hell. It's just a different looking hell. So these are how the animation promises might actually be used in the game. Like I might need to like pass information in or read other information to make a decision. And as I'm doing this game, this becomes just as unwieldy and as unmanageable as callback hell. And don't mistake me for hating on promises, but when you're using them for large-scale async work, the ease of them really breaks down. And I noticed another larger issue with using promises for the animations. So the whole point of the Tamagotchi game is that you interact with the Tamagotchi. So at some point, I need to suspend the idle animation to handle a user-generated event. So I create a queue to hold pending events, and if there's a pending event, I'm going to return a function called handleEvent. So that's going to terminate the loop. Okay, apparently we're done using the mic. So that's going to terminate the loop, and we're going to start handling the event. So handleEvent is going to take the first event off the loop, and it's going to run it. And when that's done, it's going to restart the loop. If there's another pending event, it's going to handle that. In other words, we go back to the idle animation. And this does not work. So you can see I'm requesting to feed the Tamagotchi, but that animation is delayed. The idle animation has to complete first, and then the other animation will happen. And this can take upwards of 7 to 8 seconds. So this is not going to work at all. What I need is to actually cancel the promise that's running the idle animation. Except you can't cancel a promise. So you can throw errors in promises, you can catch those errors, but you can't actually cancel a promise. All of your attached.thens are going to fire. So think of promises as unbreakable vows. Rest in peace, Nate. Loved him. Okay. So what I want is to pause an animation and yield to an event. I want to pause an animation and yield to an event. Okay, and that sounds a lot like a generator. So generators are really amazing, and that's because they're code that can be paused. So all the code that you write is run to completion. Once it starts, there's no pausing it. Even when you're doing async work, you're throwing it onto the loop, and it's going to come back around. But with generators, you can actually pause and resume code. So let's take a look at them. So this is a generator. And I know it's a generator because it has an asterisk next to the function keyword. And inside the generator, you'll see a keyword yield. That's a very special keyword in generators that means pause. To use the generator, we're going to call it, and that's going to return the generator object. And on this object is the .next method, and that either starts or resumes the generator. And it returns an object with 2 keys on it. If there's a value to the right of the yield statement, it's going to return that as the value. So you can see on the first call of next, we're getting value 1. That's because we're doing yield 1. And that's also going to return if the generator is done or not. That's going to be a simple true or false statement. So you can also yield with no values. Yield just means pause, so you don't need to send a value in. If you don't, then the value is going to be undefined. And then as you can see, we still get done false because the generator still has more things to run. We call .next again. We're yielding 3, so we get value 3, done still false. When we call next again, there's nothing else for the generator to do, so now it's complete. The value is undefined and done is true. You can also pass values into a generator's next function. And you'll notice that we're doing that here in the second call to next. And this seems really odd at first, like why aren't we passing it into the first one? When you call next, you're telling the generator like, do whatever you need to do until you see a yield statement, and then pause. So there's actually nothing for the generator to do until it sees that yield statement. So it hits that yield statement, and then it pauses. Then, on the next call, whatever we pass in to next will take the place of where the yield is. And now the rest of this code can run. So that assignment to the variable will now run. So num is now going to equal 2. We're yielding out 2 plus num, which will be 4. Generator's not done yet. Now we do 4 plus num, 6. Now we call next again, and we're done. You can also create a generator that runs for forever. So in this example, notice that we're not going to be passing 2 into next. We're going to go ahead and pass it straight into the generator function. So we're going to not have to call next and put the number in there to set that. Instead, we're just going to pass it right away. And then you'll notice that there is a while loop inside of this generator. It says while true. So this is an infinite while loop. This would crash your computer. I don't know how many of you use while loops in your daily production lives, but I do not, mostly because I usually just get into trouble with them. But with a generator, this actually isn't an infinite loop because it has the yield keyword in it. And so we're actually going to be pausing an infinite loop. So when I call next, I'm going to get value 4 done false. And that's because yield is going to pause the while loop. And then it's only going to resume again when I call next. And I can keep calling next for as long as I want, and it will keep returning values to me. You can also run a generator from inside of another generator. And to do that, you're going to use the yield keyword, but you're going to use it with an asterisk next to it. I'm going to refer to this as yield star from now on. So to illustrate this, I have a generator called outer and a generator called inner. And you'll notice that outer is calling inner with the yield star expression. So same as before. We call this function, we get the generator object. When we call next, what we expect to happen happens, right? We're yielding 1, so our value is 1, and done is false. But on the next call, we're not actually pausing at that yield star inner. You see, we're actually pausing inside of inner. And that's because yield star is a delegate. So when a generator comes across a yield star in it on a .next method, it actually goes inside of the inner generator, and it will start running from there. So it's not going to pause until the first yield in the inner generator. And then every time you call next, it will be the inner generator as long as that one hasn't completed. So this one, you can see, isn't done yet. We're yielding out B, so our value is B. Now that's done, so we go back to the outer generator. And then when we call next again on this, this will actually say that it's done. And you can cancel a generator. So there's 2 ways to do this. So in this first one, we're still using a while loop. So this should be infinite. And the first time I call next, I'm going to get what I expect value for. But then the next time I call it, it's actually hitting this return statement from inside the generator, and that will early cancel your generator. So now anytime I call next, I'm going to get done true and no value. The other option here is that I can call return from outside. So same as before, this is the infinite while loop, but you'll notice no return statement in it. Instead, we have dot return from outside, and so that will early cancel this generator. So it's really interesting to me that you can cancel a generator from inside it or from outside of it, because resuming the generator only occurs outside of the generator. So it's paused via yield and restarted via next, and generators can't call next on themselves. So something outside of it has to be doing this. And this was something I really struggled with when I started to convert my game into generators, because I didn't know who runs the generators. I'm so happy some of you got this joke. If control happens outside of it, then who's pulling the strings? And this is where coroutines come into play. Coroutines are a general control structure whereby control flow is cooperatively passed between two different routines. So I like to think of coroutines as cooperative partners. Because the generator can't resume itself, it needs a cooperative partner to help out. So this is a basic example of a coroutine. So it takes in a generator function, and it calls it to get the generator object. The inner function next response is then called. And so that actually calls the generator's next method. So this starts the generator, which will run until it encounters a yield statement. And then at that time, the generator will return the object with the value in done key. Next response will evaluate whether the generator is done or not, and calls itself with the value from the generator's response if the generator is not done. And this loop continues until the generator is done. So the coroutine is the cooperative partner to the generator. The coroutine passes control to the generator, and when the generator pauses, control is yielded back to the coroutine. And these two functions cooperatively pass control until completion. So now I can rewrite the bounce up animation as a generator and use a coroutine to run it. But this code suffers from the same problem I had earlier. The code runs too fast. I still need set timeout, and I still need promises. But my generator doesn't care if I'm using promises, so it's not going to wait for each individual promise to resolve and then resume itself. It can't resume itself, but a cooperative partner could. So I can amend the next response to handle async requests. I'm going to, instead of calling next response after calling the generator, I'm going to call a handle async function. I'm going to pass in the value of the generator's response, which is a promise. So now we can prevent the generator from resuming until the promise is resolved. When it's resolved, we call next response, and that's going to resume the generator. So using this, these two functions are now equal. Previously, we chained promises together for the animation. Now we can yield promises, and our cooperative partner, the coroutine, will handle resuming the generator when the promise is resolved. So you can do more than yield promises. You can yield all sorts of async things like callback functions, generators themselves, and more. And there's a really great framework called Co if you want to play around with the possibilities of that. I highly recommend it. Coroutines are very, very powerful. And they're powerful because they allow you to think sequentially about async code. Because the coroutine is your cooperative partner in handling the messy business of chaining and dealing with async code for you in the background, you can write your code as if it ran sequentially. So you don't have to use up any of your mind power to think about, oh, this is async, so when it comes back, it'll do this. Like, the coroutine handles everything for you. So this is the idle animation, rewritten with generators and promises. There we go. And you'll see that it's actually just the same as before. Like, nothing really changed. Like, the animation still works as it should. It's doing its thing. Good job. So I rewrote the game then with generators, like once I proved out this concept to myself. So what I did for the second version of this game was I rewrote all the animations with promises and generators. I replaced the previous animate function with a draw frame function. That takes in the sprite sheet to draw and the frame. And this function returns a new promise. So there's no inner function to run the animation. All we need in this case is to draw the frame and then delay the animation with set timeout. We resolve the promise once set timeout completes. And then our animations will yield draw frame. So here we have the dislike animation, which is just 2 frames. So it's just yielding out 2 promises that will draw either side of the dislike animation, which is where the Tamagotchi just shakes its head back and forth and is like, I don't like anything. So now we can rewrite the main loop of the game. So we're going to take advantage of canceling the generator in this. Our loop generator function will be run by the coroutine. So we can rely on it to handle any values yielded to it, async or otherwise. We'll create a variable to say the status of the generator done or not, and we're going to preset the animation to idle. So we're going to use a while loop in this. To be honest with you, this is like the only time I ever use while loops, especially while true, is inside of a generator. So we're going to use that loop to create a never-ending generator. This way, the game loop continues for forever. If we have a pending user event, we delegate to the event using yield star, and whatever the event yields will be passed to the coroutine. Otherwise, a second while loops inside of while loops, we're getting crazy. Second while loop will handle running the animation. As long as the animation is not complete and there are no pending events, this loop will yield the generator's values to the coroutine to handle. And these are promises, so the coroutine will handle any of the chaining. But if the animation is done, or there's a pending user event, the loop terminates, stopping the animation generator from running again. We'll reassign the animation to idle generator so it can start from the beginning, and we'll reset done to false. On the next iteration of the outer while loop, pending will be true and will handle the user event instead. And we're going to work on feeding the Tamagotchi, so this is what our user event is going to pass into the queue. So if the Tamagotchi is not hungry, we're going to use yield star to delegate this to the dislike animation, which you can see. If the Tamagotchi is hungry, we're going to decrease the hunger, and then we're going to use yield star eat to show the eat animation. And now it is time for the final reveal. Will this work? Spoiler alert. Yes. Okay, so I'm going to select the menu, I'm going to say please feed it, and it just goes ahead and starts chomping. Yeah. Okay, I'm going to do it again. Press feed. No, not hungry. Disinterested. No. And that is what Tamagotchis can teach you about generators.